Hi. Okay, we're resuming the session. That's 5 minutes late. So our first speaker for the afternoon session is Emmanuel Candes, and there's the title: Near Ideal Model Selection by L1 Minimization.
Thank you very much. So I'd like to thank the organizers for inviting me. And so I'll try to contribute to the discussion about P larger than N at a fairly theoretical level during this talk. And I want to present very recent work that we just completed with a graduate student of mine at Caltech, Yaniv Plan. And so in this talk, we're going to discuss very elementary things. And so we're going to look at estimations in high dimensions with a linear model. So we have, just to set up notation, things that everybody knows. We have a vector of observations, Rn, which is available to us. And then we have a design matrix X with n rows and p columns. This is a data matrix that is also known. And then we have a vector of stochastic errors, whereas the zi's we're going to assume are Gaussians, but they don't have to be. Okay, so classically, this has been hammered several times. The number of variables is fixed. The numbers of observations goes to infinity. And so if we look at statistical textbooks, they will deal all with asymptotics as n goes to infinity. But technology has changed tremendously, and now we're faced with very challenging problems in which n is as large as p, or actually p could be much larger than n. And I think that's what brings us together here, is to discuss exciting opportunities raised by this situation. Okay, so just to give you an examples of things that I have been working on, or that my wife has been working on with p larger than n. So something has been discussed has to do with genomics, where typically when you do microarray experiments, for example, you have a low number of observations, but the number of genes that you're assaying could be easily in the tens of thousands, and you have only 100 measurements. I've been extremely involved with a company trying to do something exciting, which is try to diagnose diabetes, or actually monitor your glucose level from non-invasive measurements. And so the technology we have is essentially measuring using spectrometry. So we measure absorption or transmission lines at given wavelengths, and from these measurements we try to infer the glucose concentration in the blood of a patient. And that would be useful if we could do this well, because then you do not have to take blood samples all the time to actually monitor your glucose level. And in this example, we have many more wavelengths than number of measurements. I've been involved in applications in biomedical imaging, where we cannot acquire as many samples that we would like. I've been involved in projects having to do with hardcore engineering and the design of analog to digital converters, where we cannot sample at the Nyquist rates. I've been working on a large number of problems where really this is a real issue. P is much larger than n. Okay, so now I'd like to set up the problem of interest to me, because I think there are two real problems in this P larger than n setup and in this linear model. So we have y equals x beta plus z. And what I'd like to ask is, can I actually accurately estimate the mean response x beta? So when you look at a problem of this kind, you have two things. Either you could be interested in prediction, where you want to estimate x beta, or you could be interested in beta itself. And in this talk, I want to talk about x beta mainly. So this is not a talk about the Dendick selector. It's a talk about just trying to estimate x beta and not beta itself. And I ask whether we can estimate x beta accurately when perhaps beta is sparse, or beta doesn't have to be sparse. It could just be approximately sparse. That is, for example, when there's a sparse subset of covariates that approximates well the response x beta, I'm asking whether we can estimate x beta accurately. Okay, but because I have a practical mind, I'd like to be able to do this with a computationally tractable algorithm. I don't want to hear too much about solution that would involve essentially combinatorial search. Okay. And so as I said in the end, estimating x beta and beta when p is larger than n are very different things. Okay. So in statistics, we've had a large literature on model selection and trying to do a good job at prediction. And Foster and George have coined the so-called canonical selection procedure, where essentially most selection procedures would work as follows. You try to minimize the trade-off between the residual sum of squares, which is y minus xb squared, and a term that penalizes for the complexity of the model. And typically in statistics, we've got that this penalizing term is essentially the number of covariates that you're going to include in your model. Many model selection procedures that I know of are this kind, starting with the work of Mallows and Akaiki. And there's been a large debate in the literature to figure out what this value of lambda should be. And so early on, lambda was decided, it was decided that lambda should be equal to 2 because that's an unbiased estimate for the mean squared error. Then we had the BIC criterion, the RIC criterion, and so we have a large variety now of proposals essentially adjusting the value of lambda. And this literature is theoretically extremely powerful because starting with the work of Barron and Cover, at least to the best of my knowledge, people have figured out that if you could actually solve this complexity penalized estimate, then you would do extremely well. That you would estimate actually the response x beta extremely well. And so I've listed the key contributions to this literature, starting with Barron and Cover, Forster and Jordan, and of course culminating in the work of Birger and Massar in the late 90s and early 2000s. And of course, I'm missing a lot of references. So if we could solve somehow this optimization problem, then we guarantee to do extremely well. But the problem, as you all know, is that, of course, as interesting as this literature is, the kind of solution, computational solution of the selection procedure is not feasible as soon as p is greater than 60 to be on the safe side. And so in the world we live in, where p is routinely 10,000, 100,000, even millions, as reassuring as this is that we can construct good estimators, this is not really helpful. So as you all know, a powerful alternative to L0-based selection is L1-based selection. And so we have the lasso that we all know, where essentially you relax the L0 norm into the convex L1 norm. We know under this, in statistics, under the name of the lasso, it was proposed at the same time by Shen, Donahoe, and Saunders under the name of basis pursuit. And actually, if you go back in the literature, this exact formulation was in use in applied mathematics and in geophysics, for example, as early as the early 80s. And so, for example, it appears explicitly in the paper of Sentosa and Symes of 1986. Right, so these are L1-based methods. There are others, such as the Danzig selector, which I'm not really going to talk about. But so in this talk, we will focus on the lasso. OK. And now, just as for the L0 theory, we start to see a tremendous emerging body of work about the properties of the lasso and what we can prove about L1 methods. And I've cited a lot of work that I'm familiar with, and I'm sure there are many, many others. What's remarkable about all this work is they all came just about in the last 3 or 4 years. Now, there's really an explosion of available results about the performance of the lasso and of related algorithms. It just makes times extremely interesting. And when we look at this literature, what do we see? So what do we see? We see that when it's about estimation of x beta, we usually say extremely strong assumption, and maybe I'll discuss this in the end. So we see in typically published result that either x is almost an isometry, or that the sparsity, that the number of non-zero terms in beta must be extremely small. And so we have extreme assumption about x and the sparsity level. Or we see other things, and we've heard this yesterday, where, for example, one could assume Monday and Tuesday, where we could assume, for example, that an idealized setting where I can think of the predictors as being sampled from a Gaussian distribution. And so this is a very ideal setting because, you know, unless I design x myself just to follow, I don't know of really example where I can reasonably think about x as being IID normal 0, 1. And finally, when we read this literature, we have a lot of asymptotic results explaining or telling us what happens when p and n grow to infinity in a fixed ratio or something like this. And so my take on this literature is that there's a little bit of a gap between what is known theoretically and what is empirically observed. And what is empirically observed is that the lasso works well. But we don't have really results today that demonstrate that unambiguously. And so what I try to do in this talk is to show you that the lasso probably works well in a very broad range of situations. I would like to describe to you a setting that is not idealized. I don't want to rely on random matrix theory and things like this, and I want to give you results that are not asymptotic. Okay. All right. So to state the result, I need just a little piece of terminology, which is extremely simple. So we're going to have this design matrix, which is n by p. P typically, we should think about it from now on as much larger than n. And we're going to normalize the column to 1. We can always normalize the column to 1 since we're doing prediction after all. Now with this normalization, xi is the ith column. It's the ith predictor. We're going to introduce a very simple notion, which is the notion of coherence, mu of x, which simply measures the maximum correlation between predictors. Right, so mu of x is simply the maximum between, you take any pairs of distinct predictors, you're looking at their inner product, and mu of x is simply the maximum value of this quantity. And from now on, this is what it's here. Okay. And then we're going to have what I'm going to call the coherence property, which says that I'm going to require that the matrix of predictors, that the predictor be not too collinear. And by being not too collinear, I'm going to have a very mild assumption that says that essentially mu of x needs to be smaller than 1 over log p. That's if you take random vectors on the unit sphere and you ask what's the size of the inner product in dimension n, it's 1 over square root of n. And so this says that 1 over log p is far bigger than 1 over square root of n. So it says that predictors can be collinear, but can be correlated, but not too correlated. And you should think about 1 over log p as something like 1 over 10 or 1 over fifths. So it's a very mild assumption about collinearity. And for example, if you were to randomly sample vectors on a sphere in high dimension and wait until you get a pair that exceeds this thing, you'd have to wait an enormous amount of time. Okay. So many matrices that have been discussed in this workshop obey this property trivially. For example, if you take matrices with IID entries, but I don't want to talk about matrices with IID entries, but say you take matrices with IID entries, then the correlation or the coherence is about square root log p divided by n, which is going to be far smaller than log p unless p is exponentially large in n. Okay, so we're going to have this very mild assumption that says that the predictors cannot be too correlated and the maximum correlation is about of the order of 1 over log p. Note that this is mild because it could say that you have very sparse subsets of predictors, essentially of size 2 log p, that are linearly dependent. Right? This condition can perfectly allow to have predictors of very small cardinalities that are actually linearly dependent.
Question.
Yeah.
So you referred to an expression in your opening slide. So this doesn't hold.
It's true that in genomics this doesn't hold. Now, how much you can relax this is an open question. But what people do typically in gene expression arrays, and in fact, looking at what my wife and others are doing, is when they have a very huge matrix with very high correlation, the first thing they do is they apply clustering to actually remove some of highly collinear columns. And so you could imagine that if you have a matrix with vectors pointing in the same direction, you're measuring the same thing. So if you're interested in prediction errors, they may not help that much. And so people kind of routinely prune or weed out large matrices by applying some clustering techniques so that well, if they're highly correlated and measure the same thing, but okay, but this is something I need, and if somebody knows how to get rid of this, I'd be happy. But as you'll see in the second part of the talk, you cannot get rid of this, really. Okay, so now I want to emphasize a very important viewpoint. I'm not interested in worst case performance. That is, I'm not out there to get the lasso to fail. That is, that I'm interested in, as I said at the beginning, I want to reconcile theory and experiment. And I want to know, in a majority of cases, what's the typical performance of the lasso in a majority of cases. So what I'm not going to do is I'm not going to be preoccupied with, you give me an x, and I'm going to absolutely look at this x and construct the worst beta to defeat the lasso. Okay? So I'm going to have more like a statistical measure of performance where I want that in an enormous majority of cases, I want to know what happens in the majority of cases. I'm not interested in worst case performance. Now, to discuss what happens in the majority of cases, I need to give you a statistical ensemble of what are the objects I'm interested in. So we have this model, which is y equals x beta plus z. And I'm going to have a statistical description of what I'm going to call the sparse model. So I'm going to assume that beta is sparse. And I'm going to assume that I'm going to have a statistical description that says that the support of the non-zero coordinates of beta is chosen uniformly at random. That is, I don't have any bias towards a specific subset of predictors. So all predictors are equally likely to be in the model. I don't have a priori bias towards any of the predictors. And second, the signs of betas are independent of each other, and they take the value plus or minus 1. Again, what this says is I don't have bias towards the kind of predictors that are likely to enter the model, and I don't have any bias as whether they're going to contribute positively or negatively. Okay, I'm going to make no assumption on the amplitude. So okay, I have a uniform model for choosing the predictors, and then a uniform model to choose the signs. And I make no assumption on the amplitude. Okay, so now with these two things, we're going to look at the lasso with a specific value of the regularization parameter, which I'm going to take to be 2 times square root 2 log p. The results that I'm going to show you hold with other multiple of square root 2 log p, but for the sake of simplicity, I'll just be very concrete and say 2 times square root 2 log p. Okay, so our first result is this. It says that if I have a matrix of predictors that obeys a coherence property, again, keep in mind that predictors might be actually highly collinear. I mean, that sparse subset of predictors could be linearly dependent. And if beta is actually generically sparse, that is, it's sampled according to the statistical model, and if the sparsity is actually smaller than a constant times the number of predictors divided by the norm of the matrix squared times the log factor, then the lasso works extremely well. And what it means to work extremely well, it shows that the distance between the response, estimated response, and the true response is within a logarithmic factor times the true number of variables in the model times sigma squared. Okay, so and I claim that this is a good result, that essentially you've got a mean squared error that is simply proportional to the true number of parameters in your model times the noise level times the log factor. And so as everybody knows, this is kind of an oracle inequality, because if you had an oracle which knew which variables were actually non-zero, like which subset of covariates are actually contributing to the response, if you knew this, then presumably you would estimate beta by simply regressing the response onto a subset of covariates that would be given to you by this genie, or alternatively, you would just project the noisy data y onto the span of these covariates, and so you would get this. And when you calculate how well you're doing, well, the trivial calculation, of course, shows that the mean squared error would just be simply proportional to the dimension, the number of covariates in the model times sigma squared. Okay, and so what we've seen is we don't do exactly s times sigma squared. We do a logarithmic factor times sigma squared. But within the logarithmic factor, what the lasso is shown to do is shown to achieve the performance that you could get with an oracle that knows ahead of time which variables are in the model and which are not. And of course, you could ask about this logarithmic factor, but as this has been made several times during this last 2 days, the logarithmic factor is essentially the price to pay for not knowing ahead of time which variables are in the model, and you cannot really get rid of this. Okay. All right, so let me give you some examples. So of course, if x is random, everything is easy, and you don't know the results I've just shown you, but just like as a mechanics, let's look at what happens. Like suppose you have a matrix with, say, IID entries, then Marchenko-Pasteur is going to say that the norm of x is, roughly speaking, p divided by n when p is larger than n. And so now you just see what this condition is saying. And this condition is saying that the sparsity level can actually be extremely high. It can be, if you ignore log factors for a moment, just proportional to the number of observations in the model. And of course, you can use more specialized arguments, because now if you assume that matrices are random, it's far easier. And so you can actually, if people care about these things, you can actually put the right thing in the logarithmic factor as well. OK, but this is not really interesting, because this is using this idealized setting that I have issue with at times. And so let's look at something which is perhaps a bit more interesting, which is something that comes up in signal estimation. And so this is an interesting problem. So we have now y, which is signal plus noise. And we would like to denoise, that is to estimate the mean of the vector y as well as we can. And I'm going to discuss something that has been studied heavily in the literature in information theory and signal processing, where I'm going to assume that the signal f is a sparse superposition of things that looks like time event spikes and sinusoids. So you see, I'm going to assume that the signal that I'm trying to recover is actually a sparse superposition of very distinct phenomena. One is a superposition of spikes, things that burst in time, and then a superposition of periodic effects, sinusoids. All right, so I'm going to have f, the signal I wish to recover, is a superposition of spikes and sinusoids. OK, so I have ortho basis for spikes. This is an ortho basis. I have a Fourier basis for sinusoids. So my problem is exactly of the form we've seen, where using these notations, and of course I'm saying that the signal f is of the form x beta. What is x? It's a concatenation of the spike basis and the Fourier basis. So it's a concatenation of the identity and the Fourier basis. What is the vector beta? Well, it's a coefficient in the time domain and the coefficient in the frequency domain that you see here. And so this is my setup. So it's exactly what we've been discussing. Now, because I have two ortho bases, p is 2n. Because I have two ortho bases, the norm of x squared is actually equal to 2. And the coherence is extremely low. In fact, this system is extremely incoherent. That is, when you look at the maximum inner product between things like this and sinusoids, the coherence is of the form 1 divided by square root of n. OK? And so now you cast the result in this language. You say, OK, so the assumptions of the theorems are valid. Is 1 over square root of n less than 1 over log p? Of course it is, et cetera. And so when you try to understand the performance of the lasso at actually doing accurate signal estimation when the signal is made up of very different things, then just applying the theorem would say that the lasso mimics ideal estimation if the number of components in your signal is smaller than the dimension of the signal times a logarithmic factor. So almost proportional to the number of observations. And of course, I discussed this for an a concatenation of two bases, essentially a time basis and a frequency basis. But this would work with a whole bunch of bases that are fairly incoherent with each other. And so, of course, this extends to very general signal expansions. OK, so now I'm going to discuss something that, at least personally, was a bit inspired by the work of Martin Wainwright on saying, can I say more? That is, can I actually find the variables unambiguously? And so now we're going to discuss the case where I is the true set of variables in the model, that is a set of indices corresponding to non-zero values of beta. And I'm asking, can the lasso actually say something about correctly identifying the true variables in the model? OK, and then we have a second result that is under the same assumptions as before, that is a coherence cannot exceed 1 over log p, et cetera, et cetera. And so the result says the following, that if you make sure that the minimum values of the betas is not too small, like essentially 6 times square root 2 log p, but I can lower the 6 probably. So if the values of the betas are not too large, that is, if somehow the coefficients are significant enough, then you can show that with overwhelming probability, the lasso actually correctly identifies the support. And not only this, it actually correctly identifies the signs. Right, so you give me a matrix X that obeys this kind of incoherence property where the predictors are not too correlated. Then if the betas are not too small, then the lasso would find the support exactly with very high probability and will find simultaneously the sign of beta exactly with very high probability. So you can do more than just having a small mean squared error. You can actually identify the model unambiguously with high probability. Okay. Okay, so now this is discussing what happens in the very sparse case when beta is sparse. But of course, in real life, at least in the world I live in, and that was mentioned several times by Professor Banks on several occasions, beta is never exactly sparse. And also, I mean, I don't like to put too much weight on what beta means because in many applications, beta doesn't have enough, even a real meaning either. So for example, in signal processing, which is my field of interest, just as we've seen before, we could have an overcomplete representation in which the signal is a superposition of waveforms that you would decide. And as I'll argue in a minute, now a paradigm in signal processing is to use overcomplete expansions because they allow wider flexibility at representing several phenomena. And this wider flexibility enhances statistical estimation, really. And so when you give me an image, first of all, an image is never exactly sparse in any basis that I know of. That's number one. And second, there is no true wavelet coefficient, or there is no true curvelet coefficient. There is no something like this. So what I'd like to discuss now is really like applications of interest where beta is never really sparse or in which beta doesn't really have a meaning. Okay. So the general approach to model selection, what is it that people would like to do? Is they would like to do, at least simply stated, they'd like to do something like this. So you select a model, that is, you select a subset of variables, and you're going to, for each model, like for each candidate model, for each subset, you're going to estimate the response by projecting y onto the model. Okay, so you select a set of predictors, I, you have your y, and for each model, you do the good old least squares where you're projecting y onto your model, and so you've got a candidate. Okay, so pi is a projection onto the span, on the plane spanned by the covariates in your model, and so you're projecting the data, and so of course when you do this, you get the projection of the true mean, which is what you're interested in, and you're also projecting the noise. Now for a given subset, you ask how well is this doing, and it's an elementary calculation to see that the mean squared error, that is the error of your projection estimate, is a bias term plus a variance term. And what is a bias term? It's simply x beta minus its projection onto the lower dimensional space plus the variance term, which is simply proportional to the number of covariates that you're selecting times sigma squared. And so in several papers, you see this idea of ideal model selection, which would be, it would really be wonderful to have a genie who could tell us I star, that is, would give us the best model to use. That is, out of all this subset of covariates, which one should I use? That is, which one actually minimizes or optimizes this optimal bias variance trade-off. Okay. And so the question is, well, this is what you'd be able to do with an oracle, and the question is, can you actually achieve this with a real estimator? And the important work of Baron and Birger and Masseur has shown that, yes, if you could solve L0 within log factor, you could actually achieve this, but that's not really practical. Okay, so now we're going to have a statistical description of our best subset, or the best subset of covariates that essentially achieves this optimal variance trade-off. And again, it's because I'm not interested in discussing worst case results. And so here we have our response x beta. And what we're trying to do is we're trying to find which plane of which dimension is actually optimizing the bias plus the variance. So geometrically, you could think about having a lot of candidate planes and actually choosing the one that is the closest to x beta and is not of too big dimensions. Okay, and just to, again, get at the statistical description of the result that I will present, we're going to assume that the subset, that is the covariates that enters the model and provides you with the best explanation or minimizes this bias variance trade-off. We're going to take a statistical description of this. We're going to say that I don't have any bias towards any subset of covariates a priori. And again, the signs, that is whether variables enter positively or negatively, I don't have any bias either, and they are plus or minus 1. Okay, and I'm going to make no assumption on the amplitude again. But I'm interested in a problem where, if you want, I'm interested in the generic subset, and I'm saying, well, I don't want to deal with worst case errors. I'm going to take a statistical model that describes all possible models, and that's my statistical model. And the one that is most natural, but I'm sure people could think about other descriptions. Okay. And the main result really is this. It says that if, again, under this assumption that we've already seen, that says that the coherence is not too large, and if the sparsity is bounded by this quantity, then the lasso really works well. And what it means to work well is that the distance between the lasso estimate and the truth is within a logarithmic factor of what you would get using the oracle. Right? So you achieve essentially within a logarithmic factor the optimal bias variance trade-off. The logarithmic factor only multiplies the variance, just as in Sarah's talk on Monday. But what it says is that generically the lasso works extremely well because it selects a model whose predictive power is as good as what you could get if you had the help of an oracle. Okay, and so the take-home message is that if the predictors are not overly correlated, and I don't want to see a correlation essentially above 1 over log p, then the lasso performs well almost all the time. Maybe not all the time, but almost all the time. Because these probabilities are really large. Okay, any questions? Okay. All right, so this is interesting in my field of interest for signal estimation because, as I said earlier, now people are not working with a fixed representation, but basically it seems that the message in the street is to actually try to combine several representations to borrow strengths from each representation. And so people would assemble dictionaries using representation 1, which could be like wavelets, and representation 2, which could be a curvelet, and 3 could be Fourier, and so on. And the idea is to use a combined dictionary by stacking this representation together and express sparsity of the signal of interest as a superposition of these different representations. And so there is a logic behind this, which I'll explain in a minute. But for the moment, let's consider the fact that it is interesting from a signal processing point of view to actually combine representation and try to find or estimate signal in overcomplete expansions. Okay, so what the result says, it says the following, that if I have a general signal expansions in which I have probably more waveforms than samples, and p larger than n, I could be interested in what in the field people call the best m-term approximation, which I'm going to call fm, which is like give me my signal f and find fm, which is the closest signal to f, but it's limited to have only m terms in the expansion. That is, that this fm is made of only m variables, like m columns of this matrix X. Okay? And so when you recast the result in this framework, we have that if you choose a model of dimension m, that is, if you were to select the best model of dimension m, the m waveform that you should use, then you could achieve a mean squared error, which is essentially the best approximation squared plus m, the number of waveforms you use, times sigma squared, just as before. Okay? And this is of interest to get close to this, because this is, if fm is close to f, if your dictionary has expressive abilities that you can get close to f using just a few terms, then this would be very small. Okay, and the ideal mean squared error is, of course, the minimum over all models. And so what the theorem that you've just seen says in this context is that if you solve the lasso, or basis Poisson denoising, as it's also called, I mean, if you solve a quadratic program which is of this form, which is a very friendly thing to solve, then accurate estimation is indeed possible, in the sense that your estimate of the signal is within a logarithmic factor of what you would be able to do with an oracle that would select for you the best waveforms to use. And so it would be the sum of the optimal approximation error plus m times the number of terms that you use in your model. Okay, and this is interesting for people working in the field, because the current attitude in signal processing is that there is no real universal representation, that several representations are good for different things. And so, for example, like people know that local cosines or sinusoids are going to be good to represent parts of an image with textures, for example. Wavelets are going to be good for things that look like point-like singularities, like my eyes and other things. Curvelets are going to be good for perhaps the geometry of an image, and people would like to take advantage of all these representation to actually extract from an image or use the fact that each representation is well suited for distinct phenomena. They would like to combine strengths to achieve accurate statistical estimation. And this point of view has been championed by colleagues of mine, especially Jean-Luc Stark at the CEA, who've shown that with combined representation you can achieve better denoising, you can do geometric separation, you can do in-painting, you can do a lot of things. And so just to show you a little bit what people do with combined representation as an interlude, like for example, here is an image which is a superposition of a cartoon and a texture part. And when you solve the lasso in a basis that is good at finding or sparsifies cartoons like curvelets, and a basis that sparsifies textures like local cosines, by looking at the part that the lasso picks in the curvelet basis, you actually isolate the cartoon part, and by looking at the part that the lasso picks in the local cosine, you can actually isolate the texture part. And so people using combined representation can enhance statistical estimation, but they can do things like this, of separating textures from cartoons. And that is the work of Jean-Luc Stark and many of his colleagues, including Mickey Elad, David Donahoe, and others. Here's another example with Barbara, where again, in a combined representation, you can extract the texture part, like the shawl and the trousers, and then the cartoon, the curvelet part would actually give you a sketch, a geometrical sketch of the image. Okay, and you can do lots of things that are more scientific, like isolating filaments from galaxies and things like that. And you can do other things, which is like, for example, here's a thing that works extremely well in an over-complete representation, where, for example, a lot of pixels are missing, and by actually finding an object with minimum L1 norm that is compatible with the data that is not missing, you actually can interpolate the image fairly accurately. Okay, so just to give you an idea that over-complete representations are becoming a big deal in signal processing. Okay, so now I'd like to go back to what we discussed before. And before we had two assumptions, essentially. And the two assumptions were, first, this coherence mu of x needs to be essentially smaller than 1 over log p. And the second is like beta is generic. That is, I don't want to deal with worst case. And of course, when you derive this result, you'd like to know whether I make this up because it makes my life easier, or there's something that, is it possible to actually not bound the coherence? Is it possible to actually say something universally for all betas? And that's what I'd like to discuss now. And so my first thing, which is more essential, is, okay, I don't have a result for all betas. I have a result for almost all of the betas, but a few could be problematic. Is it possible to look for a universal result? And the fact is, as people have commented during this workshop already, that the lasso does not work well universally. Let me give you an example that is going to make this point very clearly. So again, it's exactly the setup we had before. I have a signal that I'm going to make up with as a superposition of spikes like this and as a superposition of sinusoids. Okay, so I have two bases. I have the basis just as before of spikes, and I have the basis of sinusoids. And now my X matrix is going to be the concatenation of the spike basis and the sinusoid basis, except I'm going to do something. I'm going to remove what in engineering we call the DC offset. That is, I'm going to remove from the Fourier basis the waveform that is constant equal to 1. Okay? Now, just as before, I have this matrix X. Now I just removed one Fourier component. And now P is equal to 2n minus 1. The coherence is still the same. I claim that I have a system in which incoherence is extreme. I mean, the maximum inner product is of size 1 over square root of n. I have extreme incoherence. It's more incoherent than random matrices. And the norm is still less than 2. And so if the result I was giving you about before was true for all betas, I should be able to do well. But the fact is that I don't do well at all. And I'm going to show you this. I'm going to consider x beta, which is a constant vector. So it's a constant signal equal to 1. Right, so that's x beta. And you can do this in MATLAB or in R and anything you want. You'll see that this vector x beta is actually a very sparse superposition of things like this and things like this. In fact, here I show you the sparsest coefficient sequence, the sparsest way of making this constant response as a superposition of my variables. And so you see pretty much everybody is 0, except I'm in dimension 512 here, except only 24 coefficients are non-zero. It's extreme. I mean, it is sparse. It is a very sparse expansion. So I should be able to do well because this signal has a sparse expansion as a superposition of predictors that are completely incoherent. Now let's look at how the lasso does. So here is your vector x beta here. Then of course I add with noise. So the green curve is x beta plus z. And let's run the lasso now. When you run the lasso, you get this. Now what happens is the lasso takes y and applies soft thresholding. So the lasso makes two mistakes. In one, essentially, first of all, it doesn't select the sparse model at all. And second, it's tremendously biased. Right? So here is my constant signal, which is, again, a very sparse superposition of predictors. Only 24 are non-zero. These things are actually significant. They are like above the square root log p I was telling you about before, times sigma. All right? They're all significant. But yet the lasso, look at what it does. It selects a full model with 256 non-zero terms. And that's all what it does. And so what you can show numerically by just running the lasso, or in fact, you can write it down on paper. It's extremely simple to see that actually what the lasso does, it takes y and soft threshold. So there's no model selection happening. And then you suffer a tremendous bias, which means that the mean squared error of the lasso is horrible because it's simply proportional to n times sigma squared times 1 plus the threshold parameter lambda squared. And so it does a really, really poor job. And this is completely independent of dimension. I can do this in any dimension I want. I can make sparse signals that have 1.5 square root of n terms. So think about n is an image and is 1 million, for example. So I can do something with 1,000 non-zero coordinates, yet the lasso would find a model with 1 million non-zero, so 1,000 times bigger than what it needs to be. And so if you're interested in worst case performance, the lasso doesn't work. But if you're interested in the performance you expect if you're not malicious, then the lasso does extremely well. Now the second assumption that I have is for sufficiently incoherent matrices. And now I'm actually going to play my own game. That is, I'm not going to choose beta in an adversarial fashion. It's going to be generically sparse. That I'm not trying to pick a beta that makes my life difficult or makes the lasso miserable. But I'm asking, is it possible to have a lot of collinearity? And the answer is no, that you actually need an upper bound on the coherence. There's absolutely nothing you can do if the coherence is too large. And to show this, what we have is we have a little construction that is elementary that shows that I can give you a set of deterministic X, there's nothing random about them, that are square matrices whose size goes to infinity such that the coherence goes to 1. And when you run the lasso, you can show that for almost all the betas, or at least 30% of them, when you look at the performance of the lasso divided by n times sigma squared, it goes to infinity. And that is that if you're trying to get rid of the coherence assumption, if you have to try to have too much collinearity, things could go fundamentally wrong. You can actually go to plus infinity. So these two conclusions, I mean, the conclusion of these two examples is that, I don't want to send a pessimistic message, but the conclusion is that if you're trying to find a result that holds universally, it's bound to be extremely weak. And it does not describe what we see when we run experiments. And if you try to have matrices that have very high correlation, then the lasso is generically bad. Okay. Now, some people talk about proofs. I can't really tell you how these things are proved. It's what you have to understand is you have to understand properties of subsets of covariates. Things like, if you give me a subset of covariates, Xi, is this the submatrices, is it well conditioned? Is it orthogonal to the rest? And it's fairly delicate. And to prove these results, we used the result due to a wonderful colleague of mine, Joel Trupp, who actually kind of studied things like this. In fact, what he's found is not exactly new. What Joel did, it was extremely brave and went ahead and unearthed some very deep results from geometric functional analysis, which is a fascinating field. And the insights that one can get from geometric functional analysis for issues in signal processing or numerical analysis are just phenomenal. And so essentially a lot of the proofs that we use relies on deep ideas that have been developed in the 80s and the 90s by people like Bourgain and Safiri, by Mark Rudelson in the 90s, and we use extremely powerful machinery to actually get to what we want. Okay. So in the last 5 minutes, I want just to, so I changed a bit the talk because there was so much emphasis on the lasso that I thought it would be appropriate for an audience like this to talk about what the lasso can do and what the lasso cannot do. And then I want to talk a little bit about other aspects that have been studied or that I've worked on in the last 4 years with Justin Romberg and Terence Tao, that are results that have been mainly published in the signal processing literature and essentially in the information theory literature. So when you have this linear model, y equals x beta, and again, when p is larger than n, you have a situation that looks like this. And what I've been preoccupied, intensely preoccupied in the last 3-4 years is a situation in which I want to estimate beta. Not x beta, but really the object of interest to me has always been, until a couple of months ago, beta. And so I want to estimate beta when p is larger than n, and I claim that this is a much harder problem because when there is no noise, I have to solve another determined system. But when there is no noise, the problem of estimating x beta, on the other hand, is fairly trivial. You'd have to agree with me. So I claim that it's in a way, it's a harder problem. Okay, why did we work on this? We worked on this because I've been extremely interested in ways of acquiring information efficiently. And so the work that I've been doing in the last 4 years has been essentially centered around a big theme, which is how is it possible to acquire an object of interest efficiently? That is, let's say I want to take a picture of this room and I want to have an accurate representation. I want to have a high resolution picture, but I'm not willing to make 10 million measurements because I don't have 10 million pixels. So I've been very interested in this problem of having a digital object, for example, a digital image that I want to acquire by making measurements. And so what does it mean to make measurements? It means I have sensors, AI, and AI essentially correlate the object that I wish to acquire with AI. So for example, if you think that AI is a little indicator function of a pixel, it would be just a pixel measurement. If AI is a Dirac, it corresponds to time sampling. If AI is a sinusoid, it would be like you acquire information by measuring Fourier coefficients, like in medical, resonance imaging, and so on and so forth. And I've been really interested in these problems when the number of sensors we have or the number of measurements we're able to collect is far smaller than the number of pixels in the image, for example. Far smaller than p, the dimension of the object of interest. Right, so why is this? Because, well, we may have just a few sensors. Your sensors may be extremely expensive to design. For example, like if you try to make a camera that operates in near infrared, you cannot use CMOS. You have to use other composites, and it's extremely expensive to make pixels outside of the visible wavelength range. Or measurements can be very expensive. I've been working on projects where you try to see inside fuel cells by neutron scattering, and believe me, neutron scattering is a very expensive process. You can only make a few measurements. You cannot make a lot. I've been interested in applications where the measurement process is slow, which is typically what happens in medical imaging, where it just takes so long to take measurement that you cannot take many. And so the question is it possible to acquire signals efficiently by making a number of measurements which is far smaller than p, and if so, which measurement should we take? And so here's, for example, if you're interested in military applications or communication or electronic intelligence applications, here's a signal you wish to sense. So something that looks like this, like 3 radar pulses on top of each other. But unfortunately, you cannot afford many samples, or you cannot afford many views of this object. And so how does this connect with what we've seen? Well, okay, so you have signals that you wish to acquire, and you can always expand them in some basis in which you hope that the signal is sparse, and then you're going to measure. And so measuring means that you're going to correlate the signal, you're going to correlate the signal with waveforms AI, and because no sensor is perfect, you're going to have to add noise to it because of imperfections in circuits that we're designing and many, many other things. And so mathematically, the problem is exactly the thing that we've been discussing, where f has a sparse expansion as a superposition of whatever you like. I make measurements by correlating this against waveform AI. And so the problem, which is to recover f, or equivalently to recover its expansion, beta, is exactly what we've been discussing. It's y equals x beta plus z, and x is this matrix that is calculating the correlation between the sensing waveforms and the waveform in which the signal is sparse. Okay, and so now, because you're interested in recovering the signal and not denoising the data you're collecting, you want to recover beta, or equivalently, you want to recover f. And of course, what saves you when you start to undersample dramatically is that many objects we're interested in are sparse or approximately sparse. Okay, and so that's why earlier with Terence and Justin Romberg, we worked enormously on this kind of underdetermined systems of equations where we have y equals x beta plus z. And so we developed solution to do accurate estimation of beta, even though we have a number of measurements that is much smaller than the dimension of the signal. And so we developed algorithms. So one algorithm is the Danzig selector, which is a very simple estimator, which essentially solves a linear program. So just like the lasso, it solves an optimization program that is not even a quadratic program. It's just a linear program. And what we've been able to show in this line of work is, under some circumstances, about the approximate sparsity of beta, that is, assuming that the signal has a sparse expansion in some well-chosen basis, then we've been able to show that under some assumption, it is possible to actually not only recover x beta, but actually to do more, which is to recover the signal itself accurately under sparsity constraints, or approximate sparsity constraint. Beta doesn't have to be sparse, it just has to be approximately sparse. Okay, and so this is a work that was written 4 and 3 years ago. where we derived various optimality results, very much in the spirit that what you've seen in this lecture. We've shown various types of vertical inequalities that even with side information, you would not be able to do much better. And so this is interesting. This is interesting because it contributes to a field called compressed sensing, where if you only can afford to make a few measurements, then the question is, what should you measure? And so we advocated the use of random sensing, or to use random matrices to sense efficiently high-dimensional signals. And so when you couple the statistical estimation part with careful design of the sensing matrix X, then you have, at least on paper, a system that is appealing, since it said that you can actually sample very little. You can even tolerate to have inaccurate measurement, and yet you can reconstruct the signal you're interested in, things like this with high accuracy. OK, so this is just not just on paper, but now it seems that there is in academia and industry a genuine interest for these things. And so I'll just conclude by saying that over the last 2-3 years, I've been deeply involved in the development of novel hardware to actually be able to design new kind of analog to digital converters. So in a nutshell, when you want to sample a signal, most devices that I know of, most electronic gadgets that I know of, relying on the Shannon sampling theorem that says that if you want to kind of acquire a signal in a certain bandwidth, let's say 5 gigahertz, then you need 2 points per cycle, where the cycles are the highest frequency. And what it says, if you want to surveil 5 gigahertz worth of bandwidth, which is what the military seems to be interested in doing these days, you have to sample, to have a circuit that is sampling the signal 10 billion times per second. And there is no circuit in the world that can do this. The thing is that signal become more and more wideband. In fact, the US has allocated 300 gigahertz of bandwidth. They get extremely wideband. And in the semiconductor industry, there is a Moore's law for computers, but there's also a Moore's law for signal acquisition that is even more pessimistic, because it says that if you have, let's say, a sampler that is giving you good performance at, I don't know, taking 500 million samples per second, if you want to double this, go to 1 billion samples per second, which is very well short of needs that we have today, you'd have to wait 8 years, essentially. All right? And so people are a bit worried because, well, the engineers tell us that high-resolution samplers are decades away, and so what do we do? And what we do is we say, well, but you don't need to sample at that rate because the signals that you're interested in are sparse. They have a lot of assumed structure. And then you use all this kind of information theory and statistical theory that we have presented and that others have contributed to, of course. And you say, well, but wait a minute, you can sample far less. And so this led me to kind of be involved in massive projects where we're actually developing new generations of analog to digital converters that do not sample the way analog to digital converters traditionally sample. They operate at a far lower speed. Engineers I'm working with are very excited about the potential for these things because we can all of a sudden extend the bandwidth of signals that we can surveil. We have actually, Caltech in collaboration with a big company, we've actually developed and implemented, and we have in the lab prototypes of these things. And I don't know, I thought that could be interested of statisticians to know that if you make progress on the p larger than n, then it can realistically lead to some kind of very interesting novel data acquisition architectures. And so we developed one prototype, and we're in the process of developing two, and a full-blown receiver. And so people are excited about this. OK, so I want to conclude by saying that the lasso performs well in a broad range of problems. We have established that if you're not too malicious, it will really work well. And I hope that this can address the gap between what I can see when I run computer experiments and what I see when I read the literature. Thank you.
questions? Sarah?
You mentioned you have there still on the board the incoherence condition, and you mentioned as an example random matrices with the identity, the population covariance matrix. Now in literature, the conditions are often on the population version. So if that's the identity, it's trivial. So
Sure.
okay. But another point is then, suppose it is random, then maybe you want indeed to predict at a new x. So then this measure that you use.
Right. I mean, if you want to deal with random design, it's a bit of a different game. You can apply this, but you can tackle all the questions that are having to do with random design using very different ideas having to do with what we've heard on Monday and Tuesday.
So is it similar or is it different?
It's different. It's very different. Like for me, you have to understand, I'm motivated by things like my wife gives a matrix X, and it's not sampled from anywhere. What can I say about these X? Or my colleague Jean-Luc Stark has a representation in which he has wavelets and curvelets and other things, and what can I say about this?
Yeah, but if a new patient enters the room, what can I say about the new patient?
Sure, but I'm sure that the results are generally enough to be able to recast the things that you have in mind into the random framework. Now, the question is, will the result be sharp enough? Then this I can't say at the moment.
David, I think you're next, and then Simon.
Yeah, since you brought up the historical comments, I just thought, so in Scott Chen's thesis, where the basis pursuit was introduced, the goal was pretty clear, which was to look at situations that really were overcomplete, like
Right.
concatenating multiple bases.
Yes.
And at that time, there was no thought that the method of mixing L1 and L2 was new, because John Claerbout had been doing that in maybe 1976 or something.
Yeah, 1973, Claerbout and Muir.
I'm not sure in that paper,
Okay.
but I was aware of a project
Right.
that they went after. So it never would have occurred to me that the idea, the methodology of penalization by L1 could in any sense be considered new at that time. For example, Ian Johnson and I had exactly
Sure.
considered mixed L1, L2 and eliminated. But what we did think was interesting was to take an explicitly overcomplete set and show with explicit sparsity L1 will win. And I think that was, demonstrated in several ways in that paper.
Sure.
So
And so I think what you're saying, it belongs to the kind of the literature I was referring to, that empirically, and I'm thinking about Charbing's thesis, of course, empirically we see that the lasso or basis pursuit works really well.
Right. So Rob defined the lasso in this paper at about the same time as Scott's thesis, but I don't think he had the underdetermined case in mind. I think it'd be really difficult to pull that out of there.
So it's possible. I mean, I don't know. I was a bit young at the time, so.
Sasha?
What about your prior distribution? You say that you have a class of prior distributions, in fact, such that the signs come with equal probability. But if p is larger than n, then the true beta is not unique.
Well, it's going to be unique with very high probability. That's the whole point.
Yes, but you can shift it by any vector.
No, because then it's not.
And then the sign property will
It's. But first of all, the means. Yeah.
if you shift it, it can have the signs.
No, I see what you're saying, but if the condition of the theorem holds, right, then there is only one sparse representation. There are not many. There is only one. So it is actually well defined to talk about beta. So the way, I'm not sure I understand your question right.
It's another way around.
So you make a beta by selecting a sparse subset of covariates and putting signs, right? And then I worry about x beta. How does it look like? And the question is, can I estimate this response? And what the result says is yes, I can.
Probably the correct question will be as follows. You should put your prior distribution on x beta, not on beta. And because you really don't need this beta.
Yeah, but I mean, I agree. I agree with this, but then, there are many problems in which That's what I try to do with the second part. There are many problems in which beta has a meaning, like it's a gene or something. So, but I agree. I mean, and that's what we say in the paper. We say, this is an attempt to discuss statistically what happens, and it's very likely that other people will take issue with our model and would propose perhaps a more serious model of expressing sparsity generically. And I'm pretty sure that for many other kinds of models, the same results would hold.
I think Mike, and then I think we go on to the next
Actually,
speaker.
that's the same point. Could you just make the screen appear so we can see your conclusion slide? It's to the same point, really. So,
My wife tells me I almost sound Bayesian, so.
the last slide. Conclusion. Very last slide. So the point is simply this, that I think that the previous question was simply saying, well, you've partially specified he used the term prior, a mechanism for generating sparsity.
Right.
And then you say, well, the lasso works well under
Yes.
the circumstances. But isn't it guaranteed to work better if you modify the particular estimation method and don't use the lasso, but use something else that incorporates that information in the estimation?
Well, the question is, maybe you're right. Maybe you could work better, but then the question is computationally feasible? Because if your prior is actually enumerating what could happen on an exponential number of subsets, and you try to minimize...
Okay, my question is philosophical.
Sure.
Okay.
It is possible that you would do well, but the question is, what is a computational price to pay?
Okay,
So the serious connection that's being made here is that there are prior distributions that have aspects of your prior distribution in them that people routinely use as formal prior distributions in this kind of context, and routinely do Bayesian calculations
Sure.
in models of that type. And it's an open question, and I've asked this guy a number of times to study resulting posterior estimators from this perspective and ask questions of how big a difference would it make?
Okay, I think we go on to our next speaker. Well, let's thank